Hello my learners, welcome to our channel Medha Guru. I am Shweta, your maths teacher. In this video, we are going to learn about tangent to a circle. I am going to explain you the entire concept of tangents and the theorems related to tangents. So if you want your concept of tangents to be all clear, stay with me till the end of this video. So let's get started. Let us see what a circle is. How can we define a circle? A circle can be defined as the locus of a point. What is locus? Locus means the path travelled by a point. Locus is the path traversed by a point. So the circle can be defined as locus of a point which moves in a plane in such a way that its distance from a given fixed point is always equal. It is the path traced by a moving point. This is a moving point. This moving point is at constant distance from a fixed point. So this path traced is the circle. This fixed point is called the center of this is the circle. This fixed point is the center of the circle, and this constant distance is the radius of the circle. A circle with center O and radius r. We have a circle whose center is O and radius is r. This can be denoted as CO, r. This means a circle with center O and radius r. This was the general introduction of a circle. Now, to understand what a tangent is, we are going to take a circle and a line. We'll draw a circle and a line. What are the possible situations which will arise? There will be three possibilities. First possibility will be that this line will not touch the circle at all. We draw a circle and a line, and this line is not going to touch the circle at all. This will not intersect the circle. Next possibility is that the line will touch the circle at two distinct points. Now, a circle can only pass through two collinear points. Collinear means lines, points which are in a line. So a circle cannot pass through more than two collinear points. So a line can intersect the circle at 2 points. So when the line touches the circle at 2 points, we have a special name for that line. That line is called secant to the circle. So how can we define the secant? A secant can be defined as a line which intersects the circle at two distinct points. It is intersecting the circle at two different points. This was the second possibility. Now, the third possibility is that the line will intersect the circle at exactly 1 point. We know that here the line is touching the circle at 1 point, and then this line, we have a special name for this line. This line is called tangent to the circle. This is the tangent, and the point of contact is called, this point at which it is intersecting the circle is called point of contact or point of tangency. So a tangent can be defined as a line which intersects the circle at exactly 1 point, and the word tangent is originated from the Latin word tangere, which means to touch. Next, we'll see tangent as a special case of secant. When can a secant be called a tangent? We'll take a secant to a circle which is intersecting this circle at 2 points P and Q. Next, what we'll do, we will rotate this line anti-clockwise. We'll rotate the secant anti-clockwise about the point P. We'll rotate this anti-clockwise about the point P. What we'll get? What are we noticing? We see that this point is getting closer and closer and closer to P, and finally it will coincide with P. When this line will coincide with P, this line is called tangent to a circle. So this is tangent as a special case of secant. Next we'll see the number of tangents which can be drawn through a given point. A point has been given, so how many tangents can be drawn to that circle? Now, a circle divides a plane in 3 parts. We know that it is interior of the circle, exterior of the circle and on the circle. So the points can be either in the interior of the circle, on the circle or exterior of the circle. This is the case when the point is in the interior of the circle. If the point is in the interior of the circle, number of tangents which can be drawn through this point is 0. We cannot draw tangents to the circle when the point is in the interior of the circle, because any line drawn through this point will be a secant to the circle. If we draw any line passing through this point, crossing through this point, this will be the secant to the circle. So no lines can be drawn when the point is in interior of the circle. Next is the case when the point is on the circle. There is a case when the point is on the circle. Now we know that the common thing between a circle and a tangent is just the one point, the point of tangency. Through any given point on the circle, the number of tangents which can be drawn is only 1. So we can just draw one line through the point which is given on the circle. Next is when the point is in the exterior of the circle. The point is in the exterior of the circle, the number of tangents which can be drawn to that circle is 2. In this case, P is the external point and the tangents are PT and PT1. So we can summarize as, if the point is in the interior of the circle, the number of tangents which can be drawn is 0. When it is on the circle, the number of tangent is 1. And if the point is in the exterior of the circle, the number of tangents which can be drawn to that circle is 2. Next we will see the length of the tangent. Since the tangent is a line, we have seen the tangent is a line that intersects the circle in one point. So the line does not have a length. So tangent of length of the tangent means any part of the tangent, the segment of that tangent. So we can define the length of that tangent from any point P. The point P lies in the exterior of the circle. On the tangent, if we take any point on the tangent, suppose we are taking as P, so length of the tangent will be from that point to the point of tangency. This is the length of the tangent. In this case, the length of the tangent will be PT. So the length of the tangent from the point P, say point P to the circle, can be defined as segment of the tangent from the external point to the point of tangency. This was the concept of tangents. Now we are going to see the theorems related to the tangents. Let's see the first theorem. The first theorem says that a tangent to a circle is perpendicular to the radius through the point of contact. This is a circle of center O and this is the tangent to the circle. The point of contact is P. We have to prove that the tangent is perpendicular to the radius through the point of contact. That means we have to prove this angle to be 90 degree. We know that the line segment drawn from any point to a line, the shortest is the perpendicular to it. The shortest of all the line segments drawn to a line, the shortest one is the line which is perpendicular to it. So if we prove that OP is shortest of all the line segments which is drawn to this line, so that means this will be 90 degree. So what we'll do, we'll take any other point Q and let this OQ intersect this circle at R. Suppose this is intersecting the circle at R. So we know from the figure that OP is equal to OR. Why? Because it is the radius of the circle. OP is equal to OR is the radius of the circle. Next, from the figure we can see OQ is equal to OR plus RQ. OQ is equal to OR plus RQ. Therefore, OQ is greater than OR. OQ will be greater than OR. Now we can write OQ is greater than OP since OR and OP are equal. So we have proved that OQ is greater than OP. Similarly, if we take any other points in this tangent, that line will be greater than OP. So we have proved that OP is the shortest distance from O to this line. So if it is the shortest distance from O to this line, that means it is normal to this line. It is perpendicular to this line. So we have proved the theorem that the tangent to a circle is perpendicular to the radius through the point of contact. The next theorem is the line drawn through the end point of a radius and perpendicular to it is a tangent to the circle. This is the converse of theorem 1. We have a circle with center O. We have a line AB. Let this point be point P. If we join this point, we know that OPB, which is given, is perpendicular. It's given that it is perpendicular and we have to prove that this is tangent to the circle. What we'll do, we take any other point on this line. Just take any other point in this line, and if we join this, suppose this is point Q, if we join this as OP is perpendicular to AB, we know this is the shortest distance. This is the shortest line segment. OP is the shortest. So OP is less than OQ. That means OQ is greater than OP. OQ is greater than OP. Now if we are going to take any other points, if we take any other points on this line, that will be greater than OP. That means if it is greater than OP and P is lying on the circle, it means that any other point apart from P will lie outside the circle. So there is only one point of contact between the circle and this line, that is P. So therefore this is the tangent to the circle. We have proved that this is the tangent to the circle. Next theorem, theorem 3. This is the length of tangent drawn from an external point to a circle are equal. We have been given a point P. We have two tangents PQ and PR. We have two tangents PQ and PR. We have to prove that these two tangents, the length of these two tangents are equal. We can prove this by making these two triangles congruent. Consider triangle POQ and triangle POR. First, we'll try to prove these two triangles to be congruent. So first we are getting is OP is equal to OP, which is common to both the triangles. Next we have OQ is equal to OR. They are the radius of the same circle. Next is we know that the line joining the center to the point of contact is normal to the tangents. This is 90 degree. Angle OQP is equal to angle ORP is equal to 90 degree, which is theorem 1. So we have proved these two triangles to be congruent. POQ is congruent to triangle POR by criteria RHS. 90 degree hypotenuse and a side. So if these two triangles are congruent, we know that the remaining sides and angles of the congruent triangles are congruent. So we can write PQ is equal to PR, which is CPCT. That is, corresponding parts of congruent triangles are congruent. So we have proved that if we have a point in the exterior and we are drawing two tangents to it, the length of the tangents will be equal. That is theorem 3. What is the next theorem, which is the last theorem? Again, if we are drawing two tangents from a given external point P, we know that the length of the tangent is equal. Next is they subtend equal angle at the center. These two tangents are going to subtend equal angle at the center. That means we have to prove angle, the tangent making the angle at the center is POQ and angle POR. So we have to prove angle POR is equal to angle POQ. Next, second we have to prove is they are equally inclined to the segment joining the center to that point. So they are equally inclined to the segment which is joining the center to this point. So they are equally inclined means in second part we have to prove this is equal to this. First we will see they subtend equal angle at the center. So we have to prove angle POQ is equal to angle POR. Again, we have proved these two triangles to be congruent. We will prove these two triangles to be congruent by RHS. If these two triangles are congruent, we know after proving the two triangles congruent, their corresponding angles and the sides are also equal. So we can write angle POR is equal to angle POQ after proving them congruent as they are equal CPCT. Corresponding parts of congruent triangles are congruent. First part we have proved. Next, that they are equally inclined. The tangents are equally inclined to this line. They are equally inclined to the line joining the center to that point. Means they are equally inclined to OP. That means QPO is equal to OPR. Yes, again we can prove that by, as the triangles are congruent, so we can write angle QPO is equal to angle RPO. Again, corresponding parts of congruent triangles are congruent. Here we have come to the end of this lecture. If you want to solve sums for this topic, watch out for the next video. And yes, do follow us on Instagram and subscribe to our YouTube channel Medha Guru.